In this video, we're going to look at the comparison test for convergence of a series. Now, sometimes you're given a series and you don't know whether it converges or not, but then you can show that it's bounded by another sequence that we know converges. So that implies that our first sequence converges. And anyway, so this is what this video is going to deal with. And we need two background videos, bounds on a convergent sequence of real numbers, and BV2, background video 2, is monotone sequences of real numbers. So the theorem is, let's let this series, AN, and this series, BN, be series with, so they're non-negative, and BN is always at least as great as AN. Then, if the series AN diverges, that implies that the series BN diverges. And if BN converges, then so does the series AN converges. And the proof is following. Let SNA be the partial sum of this series, and SNB be the partial sum of this series. And note that for each n, the partial sum of B is always greater than or equal to the partial sum of A. Since the series AN diverges, so does this sequence, S of n of A. Thus, for a given A, so when it diverges, it means it goes to infinity. So given any number that's really big, there exists an n such that n greater than n, this partial sum always gets above that number m. That's how you define divergence. Now note that S of n of A is greater than m. That's because this diverges. But we just showed, we know that S of n of B is always bigger than or equal to S of n of A. So that says this partial sum diverges. And since the partial sum is linked to the series, that implies that the sum of the BNs diverges. And then we're done. So when AN diverges, so does the series BN. Now, part 2, by background video 1, that's bounds on a convergent sequence of real numbers. Since SNB, remember we're assuming that BN converges, so this partial sum is convergent. And since it's convergent, it is bounded by some m. So m bounds S of n of B. Now note that Sn of A is also bounded because the partial sum of A is less than or equal to the partial sum of B, which is bounded by m. So S of n is bounded. Now by background video, the monotone sequences of real numbers, then S of n of A is a bounded monotone increasing sequence, and thus it is convergent. Now, if the partial sum of A is convergent, that implies the series is convergent, and that's what we wanted to show. That if the series BN is convergent, so is the series AN is convergent. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. Please like the video, subscribe so you don't miss the next one. Thanks. Bye.